Likewise, I could combine that one with that one, to get one that travels in that direction. So each of these wavefronts also gets generated and will also propagate through the tissue. Probes have to be designed very carefully to ensure that the power in these grating lobes, as they are known, is as low as possible compared with the power going straight down. But they can't be completely eliminated. So we can calculate the angles at which these grating lobes occur. Consider this right angle triangle here, where A is the width of each element, assuming these elements are right up against each other, and the separation between these elements is equal to the width of each element. This distance here is the distance between two two peaks in the pulse profile, which is equal to the wavelength, and that is lambda. So you can see there that sine theta equals lambda over A. If we combined this with the 0th one, with the 2nd one, with the 4th one, we could then get another right angle triangle where this length is 2 lambda. So there's also the possibility of getting a wavefront which travels at an angle equal to sine theta equals 2 lambda over A. Likewise, we combine the 0th with the 3rd with the 6th, where that is 3 lambda, and so on. You can keep doing that until it surpasses 90 degrees, and then that no longer becomes possible. So all the possible angles for which these grating lobes can occur is given by this equation here, where sine theta equals n lambda over A. Providing theta doesn't exceed 90 degrees, then those are possible angles at which the grating lobes can be generated at. So, suppose a linear array of length 80 millimeters consists of 100 transistor elements. If it operates at a frequency of 5 megahertz, estimate the maximum number of grating lobes produced by the array. In other words, we need to employ that equation, sine theta equals n lambda over R. So A, spacing between the elements, which we can calculate. We have 100 elements over 80 millimeters, therefore the width of each one is 0.8 of a millimeter. The wavelength is velocity divided by frequency, which is 0.308 millimeters, and n, of course, is an integer. So if you put those things into our equation, sine theta equals n lambda, we get sine theta equals 0.385 n. So the question is asking how many grating lobes are actually produced. Well, n can be any number, any integer. Well, how many different integers will satisfy that equation? Well, sine theta cannot exceed 1, meaning that sine of an angle can only be between 1 and minus 1. Therefore, it's the number of possible lobes of any values to n that will satisfy that thing being no greater than 1. Solutions are n to be 0, which is your main beam, and plus or minus 1, plus or minus 2. Now, since that is our main beam, there are 4 other lobes. There are 4 lobes, 2 on each side, that can exist for this array.
So would you be wrong in saying there's 5?
Sorry?
Would you be wrong if you said 5?
No. I think if you said n equals 0 plus minus right,
Okay.
that's fine. I'd assume that you'd understand that if n equals 0, that means that
It's just, yeah.
it's going straight down. Okay. finally, the second part of question 5, so the first part of question 5 is on Old Standard. It says explain the following definitions of Old Standard intensity indicating how each is calculated. Spatial peak temporal average, spatial peak pulse average, and the spatial average temporal average. Well, just a quick reminder of why these are different, where they come from. A pulse is actually quite a complicated structure. At any instant in time, a pulse has a form something like this. Within this direction, along the pulse axis, we have the intensity profile containing these oscillations, like a stegosaurus, if you like, along there. But within the other dimension, parallel to the surface, these profiles will be quite smooth. So a pulse profile is a series of smooth discs, if you like, of different size, travelling throughout the medium. So if this is a circular transducer, then these will be circular as well. So you've got to consider that there's a series of circular regions travelling through the tissue. They might be increasing and decreasing in size as they travel. Due to this focusing here, these little discs become shorter, then they become broader again. That's what the sort of mental image you need to carry in your head, what a pulse profile looks like. As you can see, quite sophisticated. Now, from a safety point of view, if we want to be able to calculate what is the intensity at this point, what's the maximum intensity that I might be subjecting my patient to, then you need to take into account that there is this quite complicated profile. Now, to do this, we define a point within the pulse at which the intensity is greatest. And this is probably going to be at some point in the middle of the pulse. This has the greatest intensity in this direction, and this has the greatest intensity in that direction. So it's going to be some point right in the centre about there. And that is known as the spatial peak. So we define that pulse as having a point within it at which the intensity is the highest. And we also consider the fact that the pulse is moving in this direction, and where it is focused is where the pulse is smallest, and that's where we expect the intensity to be greatest. So there is no other position along the axis where the intensity is greater than it is here. So it's going to occur at the focus, probably right in the middle. So we call this point within the tissue the spatial peak. And thus, going back here, the spatial peak temporal average and spatial peak pulse average refer to that specific location, that unique location within the tissue, which we call the spatial peak. Yeah?
Says in the notes that broadly doesn't necessarily locate the beam axis to the focus.
Well, that's where it's perfectly ideal system, particularly if you're talking about phased arrays. The actual pulse profile is a lot more complicated. They're not perfectly circular. It's going to be a challenge. And also, it also depends on the tissue. Okay, so the spatial peak temporal average is equal to the time average intensity at that location. So you measure your intensity over all time, and then you divide by that time. So you've got a whole series of pulses travelling through that point. Then you say you do your measurement for 10 minutes, and you divide by 10 minutes, and that is your average intensity